Yeah, so we are beginning with the spotlight session, and the first talk is by IBM, and the talk will be given by Nitin.
So, hi, I'm Nitin, and it's very nice to be here at IAC. So, I mean, it's a disclaimer, I'm not a thoroughbred cryptographer, so I've only looked at sort of crypto related stuff as part of my work at IBM Research Lab, which is sort of almost coming up to 2 years now. So, today I'll be talking more from how we are looking at applying zero knowledge proofs in some of the projects, like in practice, how we are looking at applying several things. None of this is still in production, but at least, I mean, people are intrigued when we talk about like this can be done. So, and these are applications which are sort of different in flavor from the typical, the famous applications of zero knowledge proofs. So these are some standard flag bearers of ZKPs in the real world. I don't know how much money they're making, but at least they're raising a lot of money. So the Zcash, which is sort of anonymous cryptocurrency, so it's you can say secure Bitcoin. It uses what is called pre-processing ZK snarks. I mean, all these terms, I guess most of you are familiar, but they'll appear later in any case. So there's Monero, which also uses transparent ZK snarks, which is bulletproof. Then there's Coda, which claims to be order 1 blockchain, which like the entire state of the blockchain is essentially a few bytes, constant number of bytes, and you can be given a constant size proof that this is a valid state of the blockchain. And then there's Stackware, which uses stacks, and so all of these applications sort of prioritize extremely short proofs and very efficient verification. Technically, bulletproofs is not very efficient verification, but for the case that they do range proofs, it works pretty fast in practice. But we have sort of use cases with different flavors. So, I mean, in fact, there will be no blockchain directly involved here. So, if a distributor sort of wants to prove to downstream clients that he has fulfilled their orders based on his supplies, so he has fulfilled them in sort of in an impartial manner. So, like if I ordered first, I got according to supplies, I got my supplies first. Like he's not being biased, and assume that all this information is not publicly shared. Then how does he convince his downstream supplier that he has supplied? Or there could be a generic cloud document service. So it allows users to maintain documents in plain text or privately as hashes. And how do you prove to somebody that you want to prove some assertion about a document to some interested party where you don't have the document in plain text? So for these use cases, we sort of need a better balance of like flexibility, like which assertions can you prove, and proving time, proof size, and verification time. So it's not just about having a very short proof or an extremely efficient verifier. So I'll just mention the problem concretely. So it boils down to this. So given a public algorithm A, prove that running A on some private data D produces the output O, right? So that O is the result of computing A on D. To ground the data, I mean, proving anything on random data is useless. So to ground the data, we also assume that A produces the hash of the data, so against which typically the verifier will verify the claims that you're making. So A also computes hash of the data, which you can think is part of the output O. So there is some interesting computation on the data. So if data is a graph, the interesting part could be the shortest path or diameter of the graph, and the hash would be there to essentially bind which graph you're talking about. So, okay, so what are the key challenges? First, one manner it differs from the earlier applications is the algorithms may not be known a priori. So it's not a verification of a fixed circuit which you are doing time and again. Then there's a problem, how do you translate the correct execution of A to a circuit satisfiability, which is typically what is used by the zero knowledge protocols, right? And finally, which hashing scheme do we use to produce the hash of the data? So we have two considerations, security and portability. So very often the most efficient scheme may not be the one that we would use. So like a lot of protocols come up with have a commitment scheme, let's say Peterson commitment, which is natively, which is efficient under that protocol. But since we would be hashing things like maybe invoices or something, and you want the hash to remain valid, maybe even across protocol upgrades. So very often we don't want to tie the hash to the protocol itself. So very often we'll be using standard, SHA functions or to produce the hash. So that's it. It's a typical workflow. So you have a property of interest, A, it's the algorithm. You use a compiler to get circuit representation of A. Then, and to instantiate the protocol for non-interactive setting, we need a common reference string, which may or may not need the circuit representation. There's a dotted line there. Okay, so very broadly, for this setting, like you want to prove an arbitrary algorithm on some private data, any increase in efficiency in compilation or a better protocol, both of the things benefit us, because a better compiler would produce a shorter circuit representation for the same algorithm, while for the same size of the circuit, a better protocol would give you, better scalability. Okay, so I'll broadly classify. So this common reference strings and circuits, like we typically have two kinds of common reference strings, and so we'll call a CRS as flexible if it can supports. So one CRS can support several circuits. So otherwise we'll just call it rigid. And similarly, as for a circuit also, we'll say it's flexible if it can verify several computations, or otherwise if it verifies just a fixed computation, we call it rigid. So intuitively, for our thing to work, one of the things should be flexible. Either the CRS is flexible or the circuit is flexible to support, because you don't know the computations a priori. Okay, so this, like, these are not all the protocols, but roughly how they fit into the CRS and setup matrix. So updatable, you can think. So last two are sort of, you can say CRS is flexible, as in it can support many different circuits. So for trusted setup with the circuit specific setup CRS, we have Pinocchio and Groth 16, so they produce extremely short proofs. Then we have this, I think, very current. So updatable CRS is a notion that has come like its last 2 years, where you have a universal CRS which is generated by the trusted party, but you can specialize it in a non-trusted way to a circuit specific setting. I haven't had I haven't explored any of these in sort of because they're not available in code as of now. I think probably Marlin is available. And then you have universal, so you have protocols like Ligero, Aurora Bulletproof. So essentially you can do the setup which works with every circuit. So the rest of this talk is sort of going to be like whatever we have explored, how these things perform in practice. But just a bit heads up. So I said, so there are two kinds of what I call rigid circuits. So you can write a program P, which in some high level language, which has a limited control flow and essentially no dynamic memory. So all memory should be known at compile time. And you can use one of these compilers, Socrates or from Pinocchio toolchain, and essentially get a circuit which represents this flattened program. And the size of the circuit is essentially flattened. There is another work, so this TinyRAM work, which can model programs which have data dependent flow control and dynamic memory. And so the number of steps the program takes is bounded by T. So there's a TinyRAM compiler which will compile it to a TinyRAM program P dash. And then you have a circuit which represents execution of this P dash on sort of TinyRAM instruction set. So essentially this circuit shows the correct execution trace if you executed this program. The novelty here is that they do not explicitly model memory as part of the circuit, but somehow they still make sure that the memory accesses were consistent. But anyway, both these circuits are for a particular program, so they cannot be used with any other program. So we have two varieties of sort of generic circuits. So the first one is what is called simulates a von Neumann architecture. So you have a so this circuit can take a machine description and a time bound, and it can produce a universal circuit C, which can verify the correct execution of any T-step program sort of. But the universal circuit itself is sort of quasi-linear in the time bound. So when you want to specialize it to a specific circuit, you take that program, compile it, and P dash is essentially given as input to this universal circuit. So you can think of this as an FPGA, which you can make FPGA behave as a particular circuit once you supply it some input program. So essentially, if you remove the time boundedness, so what you get is recursive proof composition. So you can verify execution of an arbitrary program with just one circuit. So arbitrary means it's a polynomially bounded, but so you just take the machine description and generate a universal circuit, and then when you have a particular program, you compile this program to sort of a program on this machine, and you can give this program as an input, and so the circuit will essentially verify the correct execution of this program. So both these schemes sort of go, roughly how they work is this: the universal circuit verifies that each instruction of the state of the machine is correctly derived from what instruction was read. So essentially you can say it simulates the circuit for the CPU or the machine that is executing this program. Okay, so what about, so as I said, so the last two circuits are sort of feasible, as in they can verify several computations, and the first two the circuits. So for our problem, so this is like L1, L2, L3, L4, so lowest is so L1 and L2 are sort of circuits which verify a specific program. L3 and L4 sort of can verify sort of broader class of programs. So there's just a matrix of how this problem of showing execution of an arbitrary algorithm on some data is feasible with. So with trusted setup, you cannot work with specifics when both the CRS and the circuit is sort of specific, because then you can only do one sort of for one setting. But you can use universal circuits with a specific, like circuit specific setup. You generate CRS for the universal circuit and use it, or you can use updatable CRS with the sort of rigid circuits. So every time you have a new circuit, you will have to specialize this. Sure. Yeah. Yes. No. So I never said it's circuit specific. I count it as universal. So there is a universal part of the CRS, but it has to be specialized to a particular circuit. Okay, so which, so I don't know. So Sonic and Marlin, I think you have to specialize it. So there is, yes. Yes, but you're saying for a new circuit, you don't have to specialize. So there's no indexing step. Okay, so from the paper I read, there was an explicit indexing step. Okay. Okay, sure. So yeah, so maybe what Chaya is saying is, yeah, we can talk. So maybe that's another option, but yeah, from what I know, there is the indexing step. So yeah, then it's maybe fully universal. A transparent setup, of course, I mean, first three circuits are all first class circuits, so they can be used with any protocol. So you can use them with transparent setup also. Last one I've just left because I do not know if recursive proof composition is possible in the transparent setup. So this is some concrete performance numbers. So both of the protocol performance, which we have observed when we have been working, and the so this is the only part of the matrix I could actually experiment was in a transparent setup with circuits of type L1 and L2. I could not do L3 and L4 because I cannot get hold of the tiny RAM compiler, and updatable CRS because it's still the code is not many of them don't have implementations as of now. So typically, so we benchmark these protocols. So this is for circuit size of around 0.5 million. I chose this because for this all the protocols sort of we could run on our machine. So we had a 32 GB machine. If we go to 1 million, then Aurora sort of runs out of memory. So I mean, we found Ligero prover. Obviously, the prover is very efficient, but the only drawback is probably the proof size turns out to be sort of big. And this is Ligero. I guess there were some Ligero speakers here. So this is for the big field setting. So we're not optimizing the field size based on the circuit. So the field size is a big field size. So if you think that the proofs are longer than what they ought to be, so yes, for the Pinocchio, it's 6.4 seconds, but here I have discarded the key reading time. But I mean, you cannot always assume that the keys are huge, typically 300 megabytes or something. So very often you may not be able to keep them in memory all the time. So I mean, you probably some time will get added up. So below, so roughly these are sort of numbers you get. So yeah, I mean, they may be acceptable, they may not be acceptable. So people would normally take security if it comes for free, but then if you tell them that, okay, see, 10 minutes you'll be generating a proof, maybe they're not that curious anymore. So just to also give on the compiler side, so again, I could not do with TinyRAM, but I have some estimates. But for Zockrid's compiler, so as you can see, so this is like summing over sort of a list of 100 numbers if you want to show that, you know, sum is greater than this. So you can say the hash constraints dominate in this case because you have to build the full Merkle tree, and we're using a SHA hash, which sort of has expensive circuit. So this is sort of dominated by the hash constraints. In the second case, other constraints are also a significant fraction because normally the comparison operators cost a lot more constraints. I have estimates for TinyRAM, but from their papers. So if we were to do a SHA-256 hash with TinyRAM, so the most efficient, so some implementations I dug up. So so it takes around 4,000 lines of assembly code, and what the TinyRAM claim that the compiler sort of is within 4 times of the x86 compiler. So I'm guessing that would be around 15,000 TinyRAM instructions, and I believe their bounds, like it says, the resulting universal circuit is 1,000 times the time step. So you would get around 15 million size circuit per hash gadget. So right now it looks like it is not very practically feasible. And the recursive SNARK estimate is again a claim from the paper. They say roughly they need 26.2 seconds to of prover time for each step in the program. So that also looks like it's concretely very costly at the moment. So just to summarize, so for now, transparent SNARKs plus rigid circuit is what we find most usable. So it's concretely efficient provers, and there's no trusted setup, but verification is expensive both in running time of the verifier and the size of the proof very often. Updatable CRS plus rigid circuit, so we need more experimentation on it. We don't know right now as chassis, so maybe there's specialization. I don't know, what is the typical size of the key for a time bound? Is it like huge key, or I think it's order of the size of the circuit, right? So that can be pretty big. Yeah. And general circuits, of course, they are like very expressive, but right now they're sort of concretely prohibitive. I have some sort of what we can do to make these things more efficient. So of course, the broad line is if you make any of the protocols more scalable, or you make the compilers better, you will get benefit. But some things that, so typically when you use these circuit generators, you have to write a code and they generate. But very often verification is actually faster than actually computing, right? So for example, if you were to create a static circuit for sorting, you would end up with order n square size circuit if you're sorting n numbers, if you are not allowed those memory dependent access. But you can verify that two things are sorted in sort of with an order n log n circuit. You use a switching network. So if you can, so if the libraries can support, like for some common algorithmic routines, you have a sort of a verification circuit where you can provide the extra witness, which shows that this is sorted. There's an interesting idea. This is from Bulletproof's implementation, where you can use randomization as part of the circuit. So where some variables are, you declare them, they are random variables that will be filled in by the verifiers. You think like in the Fiat-Shamir heuristic. So then you can actually, for example, you can verify if two things are permutations of each other by using this random input R. So in fact that will give you a linear size sorting circuit also. So you do this and then you just check, you prove the correct permutation and then check that the every succeeding entry is greater than the preceding. So you in fact can get order n time circuit size for sorting. This is like, maybe if you don't need the exact property, you are just happy with the input being close to the desired property, you can even use probably some algorithms from property testing, because very often they will be cheaper, like the circuits will be much cheaper. So like, if an approximately sorted sequence will do for you, then maybe you can go for that. This is a broad question, probably it's very difficult. The people who have designed TinyRAM must have thought of it. So can you get generic circuits with better overheads? And the overhead is essentially coming because you are, for each step of the program, you are essentially verifying the circuit for the machine, right? So although they have made best efforts to make that machine as small as possible, but it still sort of works out to 1000 gates per instruction. So that is all I have. Any questions, I'd be happy to take. Yeah.
Any questions? Okay, thanks, Nitin.
Sure.